in case they don't come back. Okay, negative 5 times a negative 5 would be a positive 25. Negative 5 times negative 2 would be a positive 10i. 2i times negative 5 would be a negative 10i. And then negative 4i squared. In the middle here, positive 10i, negative 10i. Those are opposites, so I don't have to worry about that. Those go to 0. What's negative 4 times I squared? Dayton. Be a positive 4 because remember, I squared is negative 1. And so this would now be 25 plus 4. So all of this comes out to be 29. So when we multiply these two complex numbers, there's no more imaginary part to them. What's that called? What specific name do these have? We did it when we were dividing complex numbers. It's called the complex. I think I heard it. Conjugate. Okay, so complex conjugates, when we multiply them, we end up just with a number as an answer. There's no more imaginary part to it. Okay, so today, this is 3.3 day 2. Remember, we were doing all that stuff with zeros, rational root theorem. Well, now we're going to expand on our zeros in a couple slides where we can have imaginary numbers as zeros, and then we're going to rebuild the polynomial. Okay, so let's do one for practice. So this is really what we did on Monday, but it was getting towards the end of the lesson. I could sense fatigue going on. So let's actually take a look at one again. Oh, Mrs. Love. Hello. No, they already know what this call is, so there's wagers going on. Okay. All right. Thanks.
Hi, you're back.
Nate Starr, Mrs. Love. Didn't say bring your stuff, so I don't know what it is, but you can if you want. Well, you can, if you're going to take it all. You can take it all and then just bring it all back. You're fine. There's no hurry. Okay, here we go. So this is from Okay, so this was from Monday, but let's do another one here to make sure we are comfortable with this. So find a polynomial of degree 3. So we're going to have some polynomial that's going to be x cubed with real coefficients, so real numbers, not imaginary numbers, real numbers, and zeros at -3, -1, and 4. But also this polynomial that we come up with, when we put -2 into it, we get -18 as an output. All right, so there's a lot of information they're giving us that we're going to need to use to construct this polynomial. All right, so let's just start out. We'll just do it in terms of x. So f of x, and we're going to use a to represent a number, a coefficient that we're going to have. So this a is the same as like standard form, ax squared plus bx plus c. This a is the same thing. A is going to represent some number. All right, if -3 is a 0 of my polynomial, what is going to be in my parentheses? X plus 3. And then I'll have x plus 1. And then I'll have x minus 4. So again, if they tell me the zeros, and I'm creating a polynomial, I'm essentially writing it in factored form, and then I'm going to multiply through to get it from factored form into standard form. Okay. All right. So with this, I have 3 binomials. I'm just going to pick two of them, I'll pick these n2, and I will FOIL these n2 polynomials. So I'm going to have x squared minus 4x plus x minus 4. All right, I'm going to simplify that, combine like terms, so this will be x squared minus 3x minus 4. Now I can multiply by the binomial, and this is kind of the tedious part. I just have to take it individually, term by term. So the x times x squared is x cubed. The x times a negative 3x would be a negative 3x squared. X times a negative 4 would be a negative 4x. And then I'm going to take the next piece, which is positive 3. So it's going to be a positive 3x squared, negative 9x, and then a negative 12. Now again, I want to look to combine like terms, so I have an x cubed, and as I'm working through this on paper, I literally cross them out as I go along to make sure I don't miss anything and I don't duplicate anything. Negative 3x squared and a positive 3x squared, those are good. I don't have to worry about those. Those are opposites. Negative 4x and a negative 9x would be a minus 13x minus 12. Okay. No. Back. It's too late anyway. The seating chart is what they go off of. The seating chart, they already know you sit next to each other. No, move up. No. Okay. It won't matter, Jack. Like the seating, they're gonna go off the seating chart that I've already given to them. Okay. All right. So, like this is important. Okay. We took 3 binomials and we multiplied them. We got this 3-term polynomial, which is just a cubic. Now we can use this initial condition that f of negative 2 equals negative 18. And so how I'd set this up, I would have negative 18 equals, all of my x values now would be a negative 2 cubed minus 13 times negative 2 minus 12. So now I'm actually putting in values, and my only unknown I have left is that a. If I worked all this out here in my parentheses, ends up just being 6. So I have 6a equals a negative 18. So therefore, a negative 3 would equal a. All right, not done yet. So that's my a. So I'm going to go back. We'll go right here to this step. So f of x is going to be equal to a negative 3 times x cubed minus 13x minus 12. Last step, because I want a polynomial with real coefficients of degree 3. So if I multiply this into each term, I'd have a negative 3x cubed plus 39x plus 36. And that is my final answer. So this satisfies the initial statement. Find a polynomial of degree 3. So negative 3x cubed is my polynomial with real coefficients. So my coefficients are negative 3, 39, 36. Those are all real numbers. There's no imaginary stuff with it. And that polynomial in the box will have these zeros. But also, if I put negative 2 into it, I get negative 18 as an output. Okay? All right, so this is essentially from Monday. This is what I was doing at the end of Monday. So it's exactly what we did. We're given these zeros, we can expand on it. Now let's bring in some imaginary zeros. Okay? So conjugate zeros. if we have some function f of x, and it defines a function having only real coefficients, if some z represents a complex number a plus bi, and that is a zero of my function f of x, where a and b are real numbers, so that it could be 2 plus 3i. That's a complex number, but 2 and 3 are real numbers. The conjugate with notation, that z with the bar over it, that's notation to represent the conjugate. So if I know a plus bi, the conjugate would be a minus bi. And that's exactly what we did in that warm-up problem. What this is saying is if you know one of them, if they tell you 2 plus 3i is a 0, this tells you that 2 minus 3i will also be a 0. Okay, so this conjugate theorem, or conjugate zero, this is actually a theorem. I should have added that on there. So this is a theorem that's already been proven that is true. If you know one conjugate, or if you know one complex number, the conjugate is also going to be the 0 for that. We'll do one example with this, and that'll be it. It's a little bit longer, just like the last example we did, but we're going to be doing it with complex numbers instead. Okay. All right, so here we go. Mason, you ready? So find a polynomial function f of x of least degree. So they're not telling me what my final degree is going to be. Well, that's no problem. I'll be able to figure that out. Having only real coefficients and zeros at 3 and 2 plus I. Okay, so I'm going to have my polynomial. We'll call it just f of x. And we'll do this one right here. We're not going to have any a value because they didn't give me an initial condition. Like the last one that said f of 2 was negative 18. There's no initial condition on this one, so we're not going to be able to figure out what a is. So we can immediately jump right away to the zeros. So if 3 is a 0, what is my binomial going to look like? X minus 3. Okay. If 2 plus I is a 0, what's that going to look like? In my factored form, essentially. So this was a positive 3, and then we'd write it as x minus 3. So it's going to be x still minus 2 plus I. Okay? Because this 2 plus I is my piece that I'm putting in here, but it's x minus that. So again, if I wanted to be the 0, if I was given this right here, and I say, okay, what's the 0? How do I make that 0? Well, if I put a positive 2 plus I in there, because 2 plus I minus 2 plus I is 0. Okay, what is another 0? Okay, so this up here with that last complex conjugate theorem, it says if 2 plus I is a 0, 2 minus I is also a 0. So keep it in this same format. We're going to go x minus, in parentheses, 2 minus I. Because again, if I put in 2 minus I for this x, 2 minus I minus 2 minus I, it's going to give me 0. That's what I want to happen. All right, this is kind of ugly. X minus 2 plus I. So I always like to write this. I'll say x and think of it as a negative 1 outside the parentheses. So this is x minus 2 minus I. I'll write it as a binomial. or I'm sorry, trinomial, 3 terms. Okay, does that make sense how I got minus 2 minus I? And then on this one, it's going to be x minus 2 plus I. Now, don't try to like trick your brain or think of a shortcut. Okay, yep, it'll be in x minus 2 minus I, x plus 2 minus x minus 2 plus I. Don't try and like create a shortcut or try to think of that. If you think of it this way every single time, x minus the 0, x minus the 0, and then expand it out, you won't go wrong. All right, now I need to multiply these together. So let's tackle that trinomial, that stuff with the i's out there. Let's leave this x minus 3 alone for right now. Okay, a trinomial times a trinomial, we're going to have a lot of terms going on. And we just take it one by one. So x times x is x squared. X times a negative 2, negative 2x. X times I, and it's going to be positive, so that'd be a positive xi. And then we're going to do the next set. We have negative 2 times x, so that'd be a negative 2x. Negative 2 times a negative 2 would be a positive 4. Negative 2 times I would be a negative 2i. And then the last one, negative I times x, would be a negative xi. Negative I times a negative 2 would be a positive 2i. Negative I times a positive I would be a negative I squared. Tedious, but take it term by term and you won't mess up. And what you should see here, a trinomial times a trinomial actually brings 9 terms in when you multiply it all the way through. So make sure you have 9 terms going on. But the good thing is some of these will be opposites and we can get rid of them. I have a positive xi and a negative xi. I don't have to worry about that. I have negative 2x and negative 2x. I can't do anything with that. I have a negative 2i and a positive 2i. Those go away. I don't have to worry about that. That's as far as I can go. So let's write out what we have. And so I have an x squared. Negative 2x to negative 2x would be a negative 4x. Negative I squared. What numerical value is negative I squared? 1. It's negative 1 times the negative 1, so it's positive 1. And I have a positive 4, so that would be plus 5. So we've taken care of all that complex number stuff. We don't have to worry about that anymore. We don't have any complex stuff going on. But we have to multiply again by x minus 3. So we're going to have x times x squared, x cubed, x times a negative 4x, negative 4x squared, x times 5, 5x. And then we have negative 3 times x squared. Negative 3 times a negative 4x, we have positive 12x. And then minus 15. Simplifying this, x cubed, x squareds, I have negative 7, x squareds, 5x, 12x, we have positive 17x, minus 15. There was no initial condition, so I'm going to stop right there. That is my polynomial. Hardest part about this problem is recognizing your zeros, 2 plus I, 2 minus I. If you always think of it as x minus, you won't go wrong. Okay, x minus what? Get that into 3 terms. Once you get into 3 terms, it's long, it's tedious, but you just multiply every single term all the way through. Start simplifying, multiply it by this final x minus 3, combine like terms, and you get to your final answer. Okay? All right, so 3.3 day 2 is in Math Excel. Due by the start of class tomorrow.